Hello, everyone. So now we're going to start in on chapter 5. This is stereoisomers. As I said in my introduction, this is probably the chapter where having a model kit is going to be the most important. The concepts themselves don't sound very difficult. They're really not all that crazy. The challenging part is translating the 2D images that we're going to be looking at into actual 3D properties, okay? So it's something that's just very difficult to do at first, and by having that sort of tactile learning experience where you can spin things around, it makes it sink in a lot more, okay? So I highly recommend you utilize your model kit to explore these principles. The first type of stereoisomer that we're going to talk about is actually one that we already talked about last week, which is the Cis-Trans Stereoisomer. So we'll sort of build off and complicate things a little bit from what we learned last time. The whole principle behind stereoisomers, though, are this idea that, where'd my pen go? This idea that the connectivity between atoms is the same, right? So they're not constitutional isomers, which had different connectivity. They have the same connectivity. The difference is in the spatial arrangement, so how those groups are arranged. This is an example here. This is actually of a chiral molecule, not a cis-trans, and we'll talk about what that is here, but you can see that all of the connections are the same, all the bonds are the same. The only difference is the spatial proximity of each. So you have this R group and this CO2 minus group that are in the same position, but now your ammonium ion and your hydrogen are swapped, okay? This is actually really important for the pharmaceutical industry. This image right here is kind of a rough drawing of how drugs actually work. They interact with our body in what we think of as like this lock and key type thing where they fit in exactly kind of like a jigsaw puzzle piece. And so you'll have drugs where one of the stereoisomers is active and heals you, does whatever it's supposed to do, and the other one doesn't work. And it's because of this right here, because this sort of lock and key type of thing. So that's why pharmaceuticals and stereoisomers are usually sort of brought up in the same scenario for that reason. Again, these are going to be different type than constitutional isomers, right? So now we got two separate types of isomers that we've learned about. The constitutional isomers, same molecular formula, but different constitution, different connectivity of atoms. So just a quick example would be something like this. They both have the same molecular formula, but a different connectivity of atoms. This whole chapter is going to be on stereoisomers. They also have the same molecular formula, but they also have the same constitution. They have the same connectivity of atoms, just a different spatial arrangement. And so we're going to see a few different examples of that. Again, we're going to start off with the Cis-Trans Isomer, something that we already talked about last week. We talked about it specifically within the context of cyclohexane, right? So here again, we have 1,2-dimethyl-cyclohexane, and we have two molecules that are the same in terms of their connectivity, but what really differs is the spatial arrangement of those methyl groups. On this one, they're on the same side, and on this one, they are on different sides, right? So which one would be cis and which one would be trans? Hopefully you guys can answer that already. Remember, cis is when they are appearing on the same side, and trans is when they're appearing on opposite sides, okay? And this is actually how you would name this compound as well, to be specifically talking about one of these two stereoisomers, is you would include this cis 1,2, and this would be trans 1,2, dimethylcyclohexane. Okay, so those stereoisomer designations are included in the name, and then you're talking about a very specific molecule. If you just said 1,2-dimethylcyclohexane, you would be referring to both of these stereoisomers. So now a new one that we're going to talk about is Cistrans Isomers of alkenes. Okay, so the same concept will apply to alkenes. Remember, alkenes have that carbon-carbon double bond. So what's so special about a carbon-carbon double bond? Carbon-carbon double bonds, any double bond really, cannot freely rotate. Remember what the pi bonds look like. The pi bonds are taking place because of overlap in these p orbitals. Well, if you tried to rotate about that double bond, you would be breaking that pi bond. So alkenes cannot rotate about their double bonds. No, nothing can rotate about a double bond. A double bond is fixed. Not only that, but also just note a good thing to keep in mind about alkenes is their geometry is planar. You have 1, 2, 3, 4, 5, 6 atoms that are all lying in the same plane in an alkene. Okay, so because alkenes don't rotate, those positions aren't exchanging, we have this same concept of cis and trans isomers. A cis isomer would be when the two groups are located on the same side of the double bond, right? So what I'm gonna do is I'm gonna take my double bond, kind of break it down the middle and see where those two groups are attached. This would be the cis isomer. And then in contrast, the trans isomer would be when those are on different sides. So again, I'm gonna look at my double bond, kind of break it in half and see that I have a methyl group on top in one and on the bottom in the other. So this would make this the trans isomer of that alkene. Okay, so just like with cyclic compounds that can't rotate about their single bonds because they're stuck in a ring, alkenes can't rotate about their rings can't rotate about their single bond because they're stuck in a ring, and alkenes can't rotate around their double bond. So we have this same concept of cis-trans isomer that's applied. So just to do some examples here, let's actually start with the alkenes because I think they're a little bit easier than the chair conformations. So this is a good time to pause and run through these if you can. It's not the hardest concept in the world, so hopefully you guys got this down. So again, I'm gonna look, here's my double bond, here's my group. By group, I mean anything other than hydrogen, right? So I have a methyl group on this side and an ethyl group on this side. They are both on the same side of that double bond, so this would be a cis isomer. In contrast, if I'm gonna look at number 3, I have a methyl group on this side, but now my ethyl group is on the other side, so this would be the trans isomer. And what about number 5? What do you think? So here, we have methyl groups on both of, the vinyl carbon is attached to 2 methyl groups, right? So it's symmetric about that, which means that these are going to be neither cis or trans. These 2 groups are the same. So if you took it and rotated it, you would get the exact same molecule. Or similarly, you could think about it, if I swapped these 2 groups, I would have the same molecule. So there's no stereoisomer there. All right, and now let's look at these chair structures and determine whether they're cis or trans. The difficult part here is you're gonna have to draw in the missing bonds, or at least that's how I think it's the easiest to do. So in this position here, I have a carbon at a peak. So that means its axial position is pointing up, and what's not drawn is its equatorial position. And likewise, on 2, I have a carbon at the valley. So that means its axial position is pointed down, and its equatorial position is what's drawn. So here you can see that these are on the same side of the ring. They're both on that up position. And so this would be cis. Likewise, on this example here, you're going to fill in, here's your equatorial position here, your equatorial position here. And so you can see that this is in the top, but this is on the bottom. So this would be the trans isomer. Okay, so that covers it for cis-trans isomers. Now we're going to talk about, next we're going to talk about a new type of isomer, which is called a chiral isomer.